fabric defection detection based on the objective points. And again, this time I think I have more time to explain it. The introduction part is the same because we need to apply some AI technique to do the inspection. And in this part, I want to show some, just like why we need to use AI and why image processing is not so good in this area. The first one is accuracy detection by the manual is only about 60% to 75% compared to the automatic defection detection, which always more than 95%. That's why I said what we have done accuracy is not so high. The second one is the difficulty about this in the research because we have too many different kinds of defects, and in different countries, the different defects also have the different name. So if we select some samples on the internet, it's also very hard because we just try to find some broken holes, and maybe in other countries it's not named in this way. But actually, as I said, most of data sets cannot use now because it just use a grid level image and it's very old. And actually, from the start, most of the researchers do some research in how to apply image processing way to collect the to extract the defects. And the disadvantages is most of the parameters are always chosen by experiments, as I mentioned. So it's very hard to you can do it in the research, but it's very hard to apply it in the manufacturing. And sometimes if we just look online, most of the extract from the industrial fabric. It's very simple. It's very simple clothes. And what we want to do is it detect the detection from a clothes company and use a different way to weave the clothes. So most of the time we cannot use a simple way to extract the defects. And we also tried some Gabor filter or some other filters to transform the image into a frequency domain and try to get some repetition parts, but it's not too good. We can extract some images, but I remember more than 50% image cannot extract. And because the last year what we have done is it's not so bad, so we got small data. Yeah, we add two more different defects in our database, and in this time I got 25 defects images in five categories. And fortunately, these 5 categories can contain, I guess, more above 95% researchers to detect the fabrics in this area. It's just a snag, Yuan thickness, Hock, and missing lines, fly-ons. Most of the researchers just focus on how to extract the defect in those images because it's maybe not the simple one, but those is the most common one. We have more data. And in this time, we also do some augmentation. And we're not just flipping. With this time, we try to cropping the image because we think we need to expand the database in another way. We need to expand it maybe 5 times or 4 times, not just the last time, just 3 times I remember. Yeah, we expand the database, and in the end, we have about 2,000 images about fabric image, defect images, but actually it's still not enough. Yeah, and we also add some noise in the image. We use image processing rig, add some ghost noise, add some salt and pepper noise. Because we need to reduce the image quality, we want to simulate like what we can get from the company. And as I said, company cannot always support a very perfect image. They just can support a colored image, and the computation cost is very important because the company cannot provide the high consuming methods to help them detect the defects. They will think it's not useful. Why we don't use the human beings to do it is much cheaper. And in this time, we change the nets. We use the CenterNet because this net is much faster than FastRCN. This net didn't use the region proposal neural network because if you propose so much anchors, it will cost a lot of time. And in this time, we just use the head map and the center of sight. We try to find where the defect center is, and then we calculate the height and weights, and then we can detect the defects. It will the accuracy about this method will less than the FastRCN because it's just it's just try to train the network to find the central points of the defects. Is very hard. It's not so easy like we just provide so much accuracy, but it's quite fast. It's faster as our machine in the end. Yeah, and it's the different parts, how to use different parts to get the defects. And to help to improvement the technique, we use the soft NMS to try to reduce the overflopping problems like the effect in this image. They just have 3 different anchors to cover the defects. But we can, if we use fixed NMS like this one, if the cover area is larger than this value, it will delete this anchor. But we cannot see in this image. In this image, I don't know how to determine the value about delete this anchor or delete this entry. So we just try to improve this NMS technique by using the soft NMS. And if the overlap image area is not so high, we just reduce the confidence of the boxes. And if the boxes is still higher than the threshold, we will keep it and think, yeah, it's still a good anchors. Actually, it's not the anchors, it's the boxes, but I think it's the same thing. Yeah, and we also improve how to think the predict box is true, because the FastRCN just think if the predict box is close to the ground truth box, it will be the true. It's considered as a true box. But actually, for this method, it's not so useful. We need to calculate the width and height. Sometimes we cannot get a very exactly position. So we think we can use the Gauss circle radius to do this part. If it's just in this, if this like this 3 different situation, if in these circles, we think, okay, it's a good result. And that's only things is the circles will not look so good because sometimes it will be small, sometimes it will be larger, and sometimes it's changed the position, but it can get the defects. So we think it's good. We can accept it. And the experiment shows that if we use soft RCN and NMS to do the to train the database, it can improve the performance. It's only, you can say it's only proved about 1%, but actually that's because only the snag image will have some defects really close to each other. So it's this 1% is totally based on the snag image. So if we show the different classes accuracy, you can see it's a very useful, but I cannot show it. And the second one is the different augmentation methods can improve the performance about the method. But the first one is cropping the image. The second one is add some noise. But it just shows if you have more data, the accuracy will be improved. This is not so useful. And this is the MAP about we use the Gauss circle radius to help us to detect if the box position is right or not. And it not means if we have much either way to get the true position, it can improve the accuracy. No, we use the same way to calculate the accuracy. It's just help us, what we have mentioned to detect if we got the true boxes is help us to train the model, not use to judge the model if it's good or not. And the snag and fly yarn also always cannot be detected so well because it's too small. and this method it cannot detect the center of the defects. It's much harder than FastRCN. And actually, this part is it shoots the FastRCN actually shoots higher than CenterNet. I guess it's a little overfitting or something else. I'm not sure because it's not used. We do not use the last paper I mentioned FastRCN network because we update the database, so we also need to update the model. And it's not important because I just need to show the speeds of the FastRCN and the CenterNet. The FastRCN only can detect 1.2 image per second, and the second one can detect about almost 18 image per second. So I think these methods can used in the real-time detection. And the conclusion is, yeah, we prevent the new methods to detect the fabric detection, and we improved some parts of these methods to get good results and improve the accuracy. And the most important thing is the CenterNet is a simple neural network, is a lightweight network. It can be, I think, can be adapted to some small microcomputers, or like mobile and mobile or some chips. And the disadvantages is if the defect is really close, the software cannot use to modify it. It will be a big error. And I think it's still good than NMS, but it's still some trouble for us to detect the defection because we don't want to see some overlapping boxes. And in the future work, we also need to, the most important thing still, we need to collect more data to update the database. So we still don't have enough data. And the second one is we think this model can do the real-time detection. So we want to test if we can input some video and to detect the fabric in the real time. And we are doing it now. And the second one is we just detect 5 kind of defects, and we still need to do more. And I guess in the company we cooperated, they still have about other 15 different defects need to be detected, but the samples they just send us about one sample for one defect, so we cannot check the database. It's very hard, so we still need to solve those questions. And that's all. Thank you.
Excellent. Thank you. Now we know about fabric defect detection more than we knew 1 hour ago with 2 different applications. And let's take some questions from the audience here.